Have you ever wondered how a completely flawless piece of software written by absolute brilliant engineers can just spontaneously blow up multi-million-dollar rocket midair? Or why a massive banking system might slowly leak thousands of dollars, literally one fraction of a cent at a time? Welcome to today's Explainer. We're looking at the invisible constraints hiding deep inside your computer's hardware. These sneaky little limits cause everything from baffling minor calculation glitches to literal real-world disasters. To help us conquer these invisible bugs, here is our roadmap. We're going to start with the concept of the finite machine, break down integer overflow and floating point roundoff, compare the two side by side, and finally look at exactly how software engineers fix these errors. All right, section 1, the finite machine. This is really the core thesis of this entire explainer. So does 0.1 plus 0.2 equal 0.3? I mean, it's basic elementary school math, right? Okay, let's dive into this because if you type this exact equation into a programming language like Python, the answer it spits out might honestly make you question your sanity. Yeah, that is the actual output, 0.3 followed by a terrifying string of zeros, ending with a 4, and it evaluates to false. So, to a computer, 0.1 plus 0.2 absolutely does not equal 0.3. It feels like cognitive dissonance, doesn't it? Something fundamental in the computer's math is going terribly wrong. But why? Well, the answer actually lies in the hardware. See, every CPU on Earth is a finite machine. Inside the CPU, the actual math happens in these tiny, ultra-fast storage cells called registers. But here's the catch. These registers aren't infinitely large. They have a strictly fixed width. You've probably heard these standard widths before, right? 8-bit, 16-bit, 32-bit, or 64-bit systems. Because this width is fixed, the hardware is physically constrained. It imposes an absolute hard limit on how big a number can be and exactly how a number can be represented. So when computations collide with these physical walls, the system has no choice. It's forced to cut corners. That brings us right into section 2, integer overflow explained. This is where we look at the first consequence of those physical walls. So integers are whole numbers. They're exact, but as we just established, they have absolute limits. An n-bit integer can only hold so much data. When an arithmetic operation produces a result that basically exceeds the maximum range of those allocated bits, you get an overflow. It's kind of like a mechanical odometer in an old car. You know, when it hits 99,999 miles, it doesn't just invent a new digit out of thin air, it simply rolls over to 0. In hardware, if you add 1 to the maximum unsigned 8-bit value, which is 255, the hardware just drops the carry bit, and the value simply wraps around to 0. And this brilliantly illustrates why software can behave so unpredictably when pushed past its limits. Now, if you think wrapping back to 0 is just a quirky little harmless glitch, let's look at the real-world stakes here. Back in 1996, the European Space Agency launched the Ariane 5 rocket. It was an absolute marvel of engineering. But just 37 seconds after liftoff, the rocket violently deviated from its flight path and exploded, destroying literally hundreds of millions of dollars worth of equipment in the blink of an eye. The investigation revealed the culprit, and it was a simple integer overflow. The rocket's guidance computer tried to convert a 64-bit floating point number representing horizontal velocity into a 16-bit signed integer. The number was just far too large for a 16-bit register. It overflowed. This unhandled exception completely crashed the guidance computer. And hey, this isn't just some exotic aerospace edge case either. Back in 2004, there was a notorious bug in the early MS-DOS file system that corrupted any file larger than 4.3 gigabytes. Why? Because the file size field was stored in a 32-bit unsigned integer, and 4.3 gigabytes was its absolute mathematical ceiling. Exceed it, and the data was totally ruined. Let's move to section 3, floating point roundoff. We're stepping away from whole numbers and entering the messy world of real fractional numbers, which introduces an entirely different type of error. Since 1985, hardware has relied on the IEEE 754 standard to represent fractions. It essentially works by chopping a 32-bit or 64-bit space into 3 parts, a sign bit, an exponent, and a significand. But there's a massive structural limitation here. Computers process data in binary, base 2, so a binary fraction can only perfectly represent numbers whose denominator is a power of 2, like 1/2, 1/4, or 1/8. But the decimal fraction 0.1, that's 1/10, and 10 is obviously not a power of 2. Just like 1/3 creates an infinitely repeating decimal in base 10, 1/10 creates an infinitely repeating fraction in base 2. Because the computer's memory is finite, it literally cannot store an infinitely repeating fraction. It is forced to chop it off, truncating the number to fit into the available bits. This is what creates round-off error. So, the absolute crucial point here is that round-off is not a programmer's typo. It is an unavoidable inherent consequence of trying to pack an infinitely precise real number into a finite box. The software is just forced to use a close approximation. Now, what's really interesting about the slide is that massive number right there. That is the actual true value of 0.1 as it is stored in your computer's hardware. It's an incredibly precise approximation for sure, but it is not exactly 0.1. And this completely solves our earlier mystery. When you ask the computer to add 0.1 and 0.2, it's actually adding these slightly bloated approximations together. When you add them up, those tiny invisible errors accumulate, finally spilling over into that highly visible 4 at the end of 0.3. With both of these concepts introduced, let's head into section 4, overflow versus roundoff, and lay them out side by side. It's super essential to have a clear mental model of how these differ. On the left, we have integer overflow. This is a problem of magnitude. The numbers are exact, but you simply run out of physical bits to hold them, causing the value to wrap around bounds. On the right, we have floating point roundoff. This is a problem of precision. You aren't running out of room for the total size of the number, you're lacking the exactness to represent a binary fraction, leading to the accumulation of microscopic errors. Now, interestingly, if you write in pure Python, its built-in integers actually use arbitrary precision. They dynamically use as much memory as needed, so they never natively overflow. However, the exact moment your Python code interacts with C extension libraries, like processing arrays or structured data, you are right back in the dangerous territory of fixed-width hardware bounds. So how do we stop rocket ships from exploding and math from failing? Let's move to our final section, Section 5, Fixing the Errors. First off, let's talk about the absolute highest stakes arena for round-off errors, your money. Imagine you're writing software for a massive retail chain, and you're calculating an 8.25% sales tax on a $1999 purchase. You multiply them, and due to round-off error, you get an endlessly trailing decimal. Now, the correct tax should be perfectly rounded to $1.65. But if a payment system accumulates thousands of these tiny floating point approximations across millions of transactions, these fractions of a cent snowball. A discrepancy that is microscopic per transaction can quickly total thousands of dollars in missing or ghost money. To prevent this, software engineers follow some strict golden rules. First, never, ever check for exact equality between two floating point numbers. Never ask if x equals y. Instead, check if they are close enough by using a tolerance, basically ensuring the absolute difference between them is smaller than a tiny threshold, like 1/1,000,000th. Second, for anything involving currency, never use standard floats. Universally, financial software relies on dedicated decimal libraries, like Python's decimal.decimal or Java's big decimal. And here is the real pro tip. Always pass financial values into these libraries as strings, not numbers. If you pass it as a standard number literal, the hardware has actually already corrupted it with a round-off error before the decimal library even has a chance to read it. Crazy, right? I want to leave you with this final, real-world puzzle. An 8-bit unsigned integer inside a piece of legacy software currently holds the value 200. A new block of code comes along and adds 100 to it. Knowing that an 8-bit unsigned integer caps out at 255, what exactly happens next to that system? Understanding these physical constraints, treating hardware not as infinite magic, but as finite machines with strict physical walls, is what separates a good programmer from a master engineer. Think about how you'll safeguard your own code from these invisible limits. Thanks for joining me on this explainer, and keep exploring.